Good morning. Am I audible?
Yes, you are.
Okay, thank you. Good morning, everyone. Thanks for joining early in the morning. I'm sure there are some people joining from outside India as well. So, greetings, everyone. We are really delighted to have Dr. Shweta Singh here today. She is an assistant professor of agricultural and biological engineering, as well as environmental and ecological engineering at Purdue University. And first of all, she's a great friend, and we have been colleagues and collaborators in my stint at Purdue a few years ago. And we have a lot of common research interests. So her area, she has worked on many things, but the area that I'm very familiar with her work is physical input-output tables and also circular economy, recycling, and so on. So she has done her engineering BTech in chemical engineering from IIT PHU, and her master's in applied statistics from Ohio State University, and PhD in chemical engineering from Ohio State University. And I think she did her postdoc in Canada, in Ontario, and then she moved to Purdue, and she has been in Purdue for the past seven years or so. And then she has published in many leading journals in the field, particularly in the environmental science and engineering. And we are really honored to have her here. So she will be talking today about physical input-output tables and how can they be applied in the context of policy analysis in general and trade policy in particular. I hope the discussion that we are going to have today, they can, first of all, benefit a lot of us. We can learn about some of the methodologies that she is going to talk about. And secondly, we can also explore some long-term collaborations with Purdue University, with Dr. Shweta Singh's group, and so on. So I again thank Dr. Shweta Singh for coming all the way and being here. Looking forward to hearing more from her. Thank you. The floor is yours.
Thank you. So, thank you. So, good morning, everyone, and thank you, Dr. Gopalakrishnan, for inviting me. It is a pleasure to be here, and thank you, everyone, for joining. So, if I can get the talk up, we can get started. Sorry?
Presentation.
Presentation, yes, please. All right. Great. All right, so good morning, everyone, again, and without further ado, we'll get started with the talk. I'm going to talk about a computational approach that we have been developing for constructing physical input-output tables that is able to model the physical economy, and then I'll be discussing a little bit of its relevance for trade policies that we can use. So most of the audience here may be familiar with this, but just for the wider audience, when we talk about economic systems, we are talking about understanding the production, how we are supplying different products, and then how does it meet with the demand. So there is two sides of the economy that we talk. And when we talk about production, there are some underlying components that support that production system. So definitely we do have labor, land, and capital, but then there is manufacturing that forms the foundation of any physical economy that is able to provide the needed goods and services at the right time at the right place. And there are definitely the regulations and policies that help in establishing the right mechanisms to enable that manufacturing for moving the supply system towards the desired outcome. And there is also the supporting distribution systems and circulation system. So Most of the time, what we are interested in the economic system is knowing what to produce, how to produce, and how much to produce, along with where is that production output being sent, and if there is any change that gets affected, then how does it get accommodated in the economy. So there is a lot of dynamic feedback that happens between the demand and the production. However, our production systems have some kind of inertia when they are being built because we are investing heavily into the capital and infrastructure. So it is important to understand how these production systems, what is the consumption demand that we are looking forward to, and we build the production systems accordingly. So going to the physical part of the economy, when we think about it, mostly we are focusing on the manufacturing part, where if we think about manufacturing, it is a complex ecosystem of different industries interacting with each other. So any single product is being manufactured requires a lot of different inputs, be it chemical inputs, be it physical capital inputs or equipment inputs. So when we think about the physical economy, we are thinking about, let's say, a three-sector economy. We have sector one, sector two, sector three, which are showing different industries. So it could be group of industries or it could be single industry. And then we think about how different flows, the Zs that we are looking at here, is different physical commodities that are flowing from one industry to another to meet the final demand. There are also green arrows, which are the raw materials that we need from the nature, which could be water, which could be any metal we are mining. And also we are considering the impact on the physical environment. So how does different waste get generated, landfill, and because there's a cost to waste treatment, but there's also cost to the human health that gets impacted by the physical economy. Along with that, because we cannot manufacture everything, there is definitely an imports and exports that gets decided. So based on what we want to manufacture for the production that we need to meet the demands, we would also be making decisions on what do we need to import and export on the long-term basis, and where do those imports and exports come from. So there's a very clear indication, or there's a very clear connection between understanding the physical economy to meet the demand and the trade policies that we are going to form for it. Of course, what we need then is this physical model so that we can understand where to invest into the trade policies. So why is all this important today? I think it's very important because of the sustainable development goals that's going on globally, and that has impact on physical flows. One key aspect is decarbonization. We talk about reducing carbon emissions, carbon sequestration, but also moving our oil and gas-based economy towards more renewables and energy, more clean energy sources, such that solar and wind, so that we can reduce the local health impact on people of generating those energy. Another aspect is circular economy, which is really thinking about the long-term sustainability of our material economy, because we are thinking about reducing the material footprint, but also producing the same amount of goods and services that can serve the demand that we are looking forward to. And some aspects of it is reusing waste as feedstock. So there's a lot of technological advancement that is needed, but it's also a lot of logistics and policies that need to be put in place so that people are actually moving towards reusing waste as feedstocks. And what we are thinking about is creating a zero waste system, because we are looking at something like a closed economy and making more out of less. So each of these transitions, when this happens from the current economic system to the future economic system, will have huge impact on how the materials are flowing, what kind of commodities we need, and what kind of commodities need to be imported or what we can export at a reasonable cost. Some of the examples of decarbonization effort, and this is more for the US economy, that I have taken from Lawrence Berkeley National Lab. And of course, one thing that's very common to the Indian economy is also huge investment into solar and wind power. That makes sense. That also calls for investment into battery technologies and the materials that are required to have sustainable battery manufacturing within India. And then there is also carbon sequestration, so a lot of CO2 emissions and recycling of CO2 into value-added feedstock. In terms of circular economy, there is two aspects of circular economy. We can talk about a bio-based circular economy or a metal-based circular economy, which are finite materials. In the bio-based, when we are talking about more circular economy like agro residues reutilization for making different products, especially people are talking about plastics and also value-added chemicals. But in material manufacturing, we can think about refurbishing and utilization of old machineries and how we can make it more useful for the future kind of technology manufacturing. So all of these would require rethinking in terms of what commodities we need to produce and at what scale. And one thing is that it touches a large sector of the economy, not just one sector, but it touches energy, plastics, pharmaceuticals, food ingredients, and also energy storage materials. So really making the foundation very different going forward. So the question that we have is that we know what we want to do, but we also want to know how do we evaluate the physical impact on material flows of all these transitions and how to inform policies that make the right policies to actually enable these transitions in the economy and enabling the right export and import from the national economy. So the way we approach this is more of a complex systems challenge. So the network diagram that I'm showing here is a physical input-output model for state of Illinois. So this is just one state in the United States. It's in the Midwest, and it's a very agro-based state. So it is very much based on soybean and corn plantation that goes into downstream processing of energy making, like wet corn milling and biodiesel, but also there's a lot of food sectors. So you can see that it's a very complex interaction. And what I did as a postdoc is that I basically sat down and looked at the industrial interconnections within the economy to map those material flows. Now I can use this material flows to look at process improvement. So if I really want to reduce the material intensity and reduce the dependency on imports, but also increase export, then I can look at the process improvement and how much material gain I can get. We can also look at the farming sector, changing of what kind of plantation is done, at what time it is done, because there's also climate change impact that affects. So we can analyze that. But we can also go to very fundamental level of changing the technology itself and like redesigning the whole system, which will become more involved because we are also talking about capital shifts in the case of technology update. But whatever we do at one node, which is the one of the industrial sector, will have impacts on cascading impacts on material flows across the economy. And unless we understand this whole overall macroscopic impact of changes in one industrial sector, we really cannot make right policies to have a sustainable economy. We might be shifting it in the right direction, wrong direction by not having insights into it. So that's why these kind of physical input output table models are very important, but they are also very cumbersome to make. So before I get into the PIOT, I would give like a very brief overview of input-output models, and a lot of economists are very familiar with macroscopic input-output model. But just in more plain terms, let's say we have three-sector economy, where we have agriculture sector, power generation, and manufacturing. And what we want to do is understand what is the impact of making something out of that manufacturing sector. So if we have that final demand, and let's say if it's a bio-based manufacturing, we use agro residues, then it will take inputs from agriculture and power generation. Similarly, there will be some extraction of natural resources for supporting that manufacturing demand in the agriculture sector, which we call as the indirect dependency on raw materials. And we can also have some cascading impact that agriculture may provide some input into the power generation if there's combined heat and power generation, but manufacturing also may need to give some capital equipment. So that way we can have a whole development of network effects just to meet one particular manufacturing demand. And once we map all the material flows, which is the matrix N here, we can see that what are the external raw materials that we need to support this manufacturing. And this A matrix right in the between is telling us how much is the interdependency between different industrial sectors to meet that final demand. We can also expand the scope to go all the way to larger Earth system scale to look at the solar energy, because that's the ultimate energy source if we go by the energy economy concept. And this will give us an idea of that how much material is required to actually produce certain amount of product from one sector, and we can do it for large scale sectors. So most of the economies have their own classification. So we follow the North American industrial classification system, which has 423 by 423 interaction. So we work on identifying that A matrix for different industrial sectors. In the mathematical term, it's a very simple matrix formula. So we have the A matrix, and X is the total throughput in the economy. And your X can be in economic term, but we also can do it in the physical term. And we are more interested in the physical term because we want to study the material intensity. F is the final demand that is going out from the economy to the consumer. And using this equation, we can use the simplified Leontief model to get the total amount of throughput needed to meet different demand. And this X captures also the imports and exports. So when we look at the table structure, we'll see that this X embodies that, and that can help us understand what is the dependency on import and export as well. So the challenge here is that when we develop new technologies, or let's say we are talking about new policies, your interactions may change and the whole dynamics of materials flows will change. So we really need this model so that we can dynamically update the A matrix to account for all those changes. But as I said, the estimation of A with good accuracy and fast is the challenge, and that's what we have been focusing on, is solving the bottleneck to use these models for analysis. So going to the physical input output, just as we have the macroscopic input output model for the economy, we have the physical model. In the physical model, what we do is that we simply replace the economic flows with Z matrix, which we call physical flows from one sector to another. So your left and your columns would be all the industries, and your rows will be all the industries, and your matrix will capture how much material is required from one industry to another for the production. Similarly, we'll have the data structure for demand, where we can look at what is the consumption and what are the different exports and imports that the industry is requiring. So that may change as we change how much we are importing or export. So that means that this table can be updated. On the lower end side, we also look at the interaction with the rest of the economy, or what we call as the natural systems as well. So how much raw material we are taking. So if you think about circular economy, also what use of residuals is there, or there's residual production and emissions. So the emissions and raw materials are really key to understand the impact of our physical economy on our natural environment, which can be a focus when we are making policies to really shift to different technologies. And what we do is then once we have these data tabulated, we check for the material balances across rows and columns. And since the thermodynamic first law of mass balance cannot be violated, we are able to develop a model that's very highly reconciled in terms of material flows. So that becomes total inputs and total outputs, and gives us an idea of what the physical economy interaction looks like. So in summary, what we are doing is we are basically mapping the whole biophysical economy for material flows. And the idea is that if we can see the system in a transparent way with good accuracy, we'll be able to design as the new policies come on or new technologies come in to see what materials or commodities we really need. And that is not being produced locally. If it's not being produced locally, we have to import. If it is being produced locally, then we also need to see what is the impact and what are the cost factors that we need to account for. So that is a brief overview of what physical input-output model looks. And I already showed this model. This is just, and the details of the model and how the economy is interacting is not important. What is important is that this is how PIOTs give an idea of the complex interaction. What we found was that this was an empirically derived model. There is a lot of complex interaction, and we can see that if we change one node, the material, the cascading impact and the structure will change. And we have used this PIOT for life cycle analysis, material efficiency for different final demand. But what I really want to focus on the challenges is that this was very slow because it took me about 2 years to collect the data for a very small number of industries in the small economy, and it is not even covering the full economy. So another challenge was reproducibility. This was developed for the year of 2012, and if I needed more data and it was not released by the census or it was not released by the Environmental Protection Agency or Geological Survey, it was very hard to estimate this. And also, if I wanted to change, let's say, a different industry and enter a new circular economy kind of scenario, automating the update was not easy. So we really don't know how to account for the cascading impact fast. So to overcome that, so I already talked about the cost. One was the time cost. We cannot really wait 2 years for finding data and develop a model and then do analysis. And also validation was hard because when we have only one data point and not really it's all senses, we don't know where actual errors are coming from. And also reproduction was very hard. So what we did was we developed a novel approach where, so I'll talk about, I'm required to notify this, so it's a US patent pending, but what it does, it overcomes the challenges identified above. And how it does is that what we did was we got rid of just being reliant on the empirical data, and we instead started from going from a very fundamental approach of mechanistic and simulation models. So instead of just looking at what material flows are going from one industry to another, we started looking at how each industry is functioning in terms of material utilization and production. So for example, if we have, let's say, a steel manufacturing unit, we can have a physical simulation model to know what all materials it is requiring and what all materials it is producing. So once we have these kind of model for different industries, then we developed an algorithm to basically map the supply and demand of different commodities in within that industrial network structure. So once that simulation models are uploaded to the algorithm, it gives us a network map of showing how different industries are interacting in terms of material flows. So here we have one industry sending a lot of material to the energy production, and then it's showing that it's giving to another. So this automation allowed us to make it very fast. So instead of waiting for the data to come to us, we build simulation models, validate those simulation models from an engineering approach, and then use the algorithm to update the network model. So it takes once the initial models are set up, it takes about 2 to 3 days, or even depending on the scale. We have done it for 10 sector economy, but if we have to go larger, I would assume that using high performance computing and all, it can be expedited much further. So the benefit of this is that it's reproducible and easy adaptability. It takes lesser time, and then we can also, because if we think of new technologies like EV manufacturing, or if we think about recycling of EVs, we can build a simulation model for that and update, and that it will update the network map accordingly because it is mapping the supply and demand of the commodities. So that way, automating this approach helps us in dynamically automating the physical input-output table generation, and we can do a lot of scenario analysis in terms of understanding the commodity need for transitioning to a decarbonized or a circular economy. So how does this work? So there is two parts to it. One is the mechanistic models to PIOT. So first we do look into each of the industrial sectors and we develop mechanistic model. What the mechanistic models does is that it utilizes the underlying physics and chemistry information of the manufacturing process. And for each of the manufacturing processes, we will look into developing the model that how different commodities are being utilized and what are the different outputs. Sometimes some industries make also co-products, which are the byproducts, which are not the main product, but are also important in the physical economy tracking, and also waste. So each of these sides, from the input side, we get what we call as the physical use table, which is here it is industry by commodity. So it can tell that what are the different commodities an industry is using. And since it's based on mechanistic simulation model, uh, which is implicitly accounting for the mass balance, we can trust the data. So that was our main uh, goal of developing a simulation model that is with an underlying physical way, so that we can trust the data. A lot of time when we get data on the large scale economy for material flows, it's not easy to trust that data. On the other hand, we get what we call as physical supply table in form of commodity by industry tables, where we are knowing that what are the different commodities that are being produced and which industry are supplying it. So once we have a physical use table and physical supply table, we combine the two using some of the transformation of based on the Eurostat. Basically, the European Commission has developed some of the approaches to develop, convert physical supply and use table into Eurostat. Of course, there are some assumptions that undergo in terms of which technologies are mapping to which commodities, but that, of course, can be updated based on what you know about the real economy. So then when we have the physical input-output table, we also can develop a Sankey diagram showing the whole network of physical flows within the economy. So going into more detail, so this is the mechanistic model and I already talked about it. So we have the commodities in this subsystem. Each of these subsystems can be modeled, and we have the inputs that are required for this sector to function, and then the outputs. The data from the input side is going to the physical use table, and the data from output side is going to the physical supply table. And we also scale each of what we call as engineering models to represent industrial operations. So if I know how much a economic region is producing at a certain scale, then we scale the model to make that output. So it is actually representative of what's happening in the economy. So that scaling part is where we need some input from the economic operations, that what is the scale at is operating, what, and in future we can also think of what scale we want to operate into. So we can also scale it accordingly. So this is one of the challenging part of the approach, I think, in the sense that we need really good simulation models. But then with the engineering community, there's a lot of simulation approaches that have been used for automotive manufacturing or for chemical manufacturing. So we are really relying on an existing knowledge base that we have that has not been connected to the economic policy making. Okay. So the next step in the algorithm is that we also balance physical supply and use table, and we have developed this approach. So first we start with the raw physical supply table, and then which may be imbalance. So we look at first at the industry level balance, because industry is based on your physical model. So it should really have input and output must be equal. And if there is mass imbalances, we check our models itself first, and if the model has some discrepancy, we fix that. Once the data is balanced, we also include import and export data and the final demand data. So if the import export data is not there, we just add it as a slack variable to estimate it. So where there are imbalances and there are unexplained imbalances, it can be added as import export data. So then we check at the, once we have added all the import export for the physical supply tables and we have both the structures in place, then we check for commodity level balance. So if there is any regional economy and there are stock changes and there are unexplained material flows for commodity, we really need to go back and forth to adjust that imbalances. And sometimes that imbalances can be from the rest of the economy or it could be import and export. So that's where there are some uncertainties that can be played around with looking at where do we want to allocate those imbalances. Once we have that, we also check for the rest of the economy, and finally we have a balanced physical supply use table. The need for balanced physical supply use table is mainly because it is we want to ensure that the material flowing in the economy and output is completely accounted for, and this is also very important to for eventually having the environmental impact. That was one of our goals for developing these models. So once we have our balanced physical supply use table, we go through a simple transformation. So we have the physical use table, which is the commodity by industry, which commodities are going to which industries. We put it in a U matrix or a U vector, and then we put a physical supply table in another vector. The transformation matrix here is basically saying that how much of that supply is coming from the particular industry. So when they are a total commodity supply, and then we calculate the Z matrix, which is the flows between different industries at Z equal to T times U. And final demand is allocated for different industries based on the transformation. And similarly, we allocate some of the exports to different industry and the imports. So this allocation part, import and export, we have just put it as a placeholder right now because we didn't have enough data. So we wanted to have the algorithm work through the import and export. But that's where if we have good information on import and export, we can supplement it with the right data. So now I'll show some results that we use. So we model the Illinois economy. We have 10 sectors, and you can see that a lot of these were farming sectors because of the nature of the economy that's operating in Illinois. And the mechanistic model that we used for farming was all the plant growth model. So that gives us an idea based on the United States Department of Agriculture. We had an idea of how much acres are harvested, how much acres are being planted, what kind of planting scenarios are there, and that gives us an idea of how much material flow is going into that agriculture sector, what is being taken out and at what time. We did at 1 year scale because we were not interested in very fine scale temporal resolution, but just an yearly scale. Then we had in hog farming, which was a different kind of sector. So for that, we developed our own model for animal growth farming. So where we looked at how much feed that animal system is taking and what is the total output, and it's kind of a logistic curve that comes out, and we aggregate the total output. The easiest sectors to model were chemical manufacturing, which we started developing very Aspen Plus, which is a very standard chemical software that is being used to look at the material flows at any plant scale. And each of these sectors, then for the state of Illinois, we scaled to match an output variable. So you can see that some of the output variables we selected were based on what the agencies were reporting so that we can validate our models that it is working really well with what actual economy is working on. We did notice some errors. So for some sectors, we had about 26% error and 15 and 18%, which we were happy with at that time because we were still developing the method. But as we go forward, we really want to reduce this error percentage between the simulation models and actual economic functioning for the material output. So that gave they gave us a confidence that this kind of approach can really automate and make us do things faster for mapping the material flows. So once we had all these engineering models developed and validated, which was the first step of the method, we then put it in the algorithm and we generated the what we call it the physical supply table and map and use table. So this is basically the physical supply table, and none of it is empirical data. It is all simulation data that has been validated. And you can see that what it is telling you is that what are the different industries in the economy and what kind of commodities they are producing along with the waste. So having an information of the waste really gives a good idea of where we can implement a circular economy. The good thing of also using this simulation approach that we could go down to the chemical composition of each of the material flows. So having the chemical composition also lets us know that this is the right commodity or this is the commodity that can have different use for the economy. The next thing was physical use table. In this table, we got what are the different commodities and which industries are using it. So there's another Sankey diagram, which gives a very detailed idea of a full map of the commodity and going to different industries that shows where the industrial dependencies on commodities are. So this can also be used in an idea of if there is a scarcity of a material, which industries will get hit most in terms of material output because they need this for production. And that can also give them an idea of pricing, that what kind of pricing would be important for the industries to maintain their production in the long term. Then we converted that into using our transformation approach into physical input output table, and this is 10 by 10, and you can see what this gives. This is the heat map showing where are the different industrial interactions. So there is an interaction between the rest of the economy with all of these industries because there was some unexplained sector that we did not model. But you can see that the urea manufacturing sector is interacting with the corn farming and other farming sector, and there is also corn farming that is giving input to the corn biodiesel and hog farming as feedstock. So this was all, we did not do anything empirical. This is all after the simulation. So we automatically get an idea of where the hotspots for interaction between industries, and we can also dig deeper into which material it is interacting in a real sense. So we can also see the imports and exports. So we did add some data on import and export that also gives us an idea of which industry in that region is dependent on imports and which industry is actually exporting. So what do we need to do to maintain that economic revenue that we are getting? No. So now I'll give you a quick demo of the tool that we have developed. So we developed this approach and then we implemented in a cloud-based tool because a lot of this work is not, we cannot do it all alone. It has to be very collaborative with multiple teams. Yeah. So can I play, I don't know, can you just play this video? Just click here. All right, so that was a quick demo of the tool. This tool is still under development, but we have got the proof of concept right in terms of like how the mechanistic simulation can automate development of these physical input-output tables that can be then used for further analysis. So we can download all the models and upload. Sharing, I think the good feature is the sharing because different people can develop models for different industrial sectors and collaboratively we can map the full physical economy instead of one person doing, which will take much longer. So then what we did was we used our tool to study the redesign to circular economy. So we had all these 10 sectors. We analyzed which industry had the highest waste generation and we introduced a recycling sector. So we introduced two recycling sectors. The recycling sector was taking inputs from the hog farm. So hog farm had a lot of waste that could be converted into manure and also some of the industry had industrial wastewater that could be recycled. So we implemented two recycling technologies and we updated the network map. So this is the heat map that shows how the new recycling sector is changing the material flows within the whole economy. So you can see that the recycling sector is sending some input to the corn ethanol because it is recycling some of the wastewater and making it useful for the industry, but it's also sending some into the soybean industry. And there is also inputs from the in terms of corn farming and pea farming because there's recycling of those manures into fertilizer. So this was just for the demo purpose, but it can be used for a lot of different industries where you want to test a new recycling technology at scale to see how much dependency on different materials we can reduce. So what happened is after the recycling introduction was that the urea sector reduced production, reduced some interaction with some of the bean farms and corn farms, so the material intensity reduced. But we can also think of it as that if there is local waste available, we can meet that we can send that excess production to as an export. So it can be a revenue generating stream by redesigning your regional economy to reutilize some of the waste locally and then sending that high value product as an export for the revenue generation. So in this case, we did not implement that kind of scenario, but we just reduced the material intensity to look at the environmental impact that reduced. So that was one thing. This is an example. So after we introduced the recycling sector, this was the potential reduction of waste in the industrial sector, and some of the sectors you can see reduced by 94% or 99%, which was really good. So that means that this economy has a huge potential. If we just introduce a recycling sector, they can reduce the environmental impact hugely. We also looked at the change in material flow. So this is delta XB before C is saying how much of the total material flow required for one unit of production before circular economy, and delta X after C is that after circular economy. So we can see that the corn farming reduced by 16%, which means that there is 16% reduction in material requirement to still meet that one unit output. And hog farming is reduced by 67%. So that gave us an idea of that how much reduction in material requirement we can expect to meet the same demand if we implement these kind of circular economy technologies, and also will help us in understanding if we had some dependency on imports, then we can how much we can reduce that dependency and by how much material. And of course, the pricing and all can be worked out after that. So in summary, now that we are coming towards an end, we developed an automated approach to develop these physical input-output generation using mechanistic engineering models. It's a really nice integration of engineering knowledge with macroscopic economic framework to understand how the economy is functioning in terms of material flows. We did some simulations to quantitatively evaluate the impact of transition to circular economy, which was one of our goals. And we also developed a prototype of cloud-based computational tool that we can use for collaboratively mapping physical economy. Of course, there's a lot of customization that will be required when we are looking at a specific economy, but there's also a lot of scale up in the cyber infrastructure that will be required. So now shifting a little bit on PIOTs and trade policies, and I have not done a lot of analysis, but this is what I think can be used and done. One is informing trade of commodities for growth of emerging technology. So when we are talking about scaling up EV manufacturing, or we can talking about scaling of solar cells, and we want local manufacturing or even the wind blades, then we can do a simulation to look at what different kind of commodities will be required. And if it is not produced within the economy, we know that that's the trade dependency that we'll have. So the mechanistic simulation models for these future technology can be used to inform what kind of trade requirement or trade agreements we would need from different kind parts of the world to actually enable the growth of these emerging technologies. And it could also be for bio-based plastics. That's very important going forward. Another thing is on informing design of circular economy to reduce imports and trace costs. So we have already done some circular economy simulations, and we did see that there was reduction in dependency on urea manufacturing. So if urea manufacturing depended on some other inputs, and maybe urea manufacturing is very self-sufficient, so that may not be the right example. But if we have, then we can project the material substitution potential in the economy, that we don't really need that much of import. Maybe we can shift to something that's more locally available. So that is how I see that these kind of PIOTs mapping of the whole physical economy can help in informing the trade policies in the long term in the right direction. And some of the ongoing and future work, we are expanding the capabilities of PIOT hubs. So we are including more economic sector. We are also in talk with some startups who want to do some analysis of whether there is a scope of implementing their technology at large scale, but also adding new cyber infrastructure to do a lot of large scale simulation. One specific project that we are working with Department of Energy is on the mapping the rare earth metals flow in the economy, because there is a lot of focus on creating circular economy for rare earth metals within US because of it is a very critical material for solar economy or the battery manufacturing, that EV cyber infrastructure, sorry, it's the EV infrastructure. With that, I would like to thank everyone, especially my funding sources. So I started the PIOT work as a National Research Council postdoc with the National Academy of Engineering. So they funded that work for 2 years, and then the National Science Foundation, the Chemical and Biological Engineering Technology Department funded it, and then Purdue Research Foundation. Also, I would like to thank my students, especially Dr. Gargia Vunova, who is now at Amazon, and he did most of the work in developing the algorithm and implementing it, like programming. So really good work, very exciting work. And Dr. Nehika Mathur and Dr. Fature, who was into input-output, and some of my current students who are now scaling up the PIOT capabilities. A lot of collaborators, so and whom I learn a lot from, and my advisors, colleagues, and professional societies like AICHE and International Society of Industrial Ecology. So with that, I would like to thank you all, and I'll be happy to take questions.
Thank you very much, Dr. Singh. It was a really very technical and very insightful presentation. So, quick question on the collaborator. Dr. Manfred Lenzen is also the developer of EORA, right?
Yes.
Yeah.
Yeah, so we have worked on industrial ecology lab. So he has what we call as virtual industrial ecology lab, which is on the multi-regional input-output.
Right.
So we have developed the US counterpart with Dr. Lenzen.
Oh, wonderful.
So Dr. Futu Fatere was visiting our lab in 2017 and 18, and now we have a very well-functioning multi-regional input-output. So I did not talk about the multi-regional input-output. That's another beast in itself, but yeah.
And that's for the US. What
Yeah, so we did US. So we have like
interstate.
Yes, we have 52 different states, and and the good thing about that approach that Professor Lenzen originally developed is that we can look at different disaggregation in the sector. So if we want a 21 sector economy or 1,000 sector economy, so some of my students are using that capability to look at if we have to insert a new sector like bio-based plastic manufacturing, or we have to look at the wind energy expansion. So that's what we are doing.
Great. So,
Hi, Vishnu here. I have a few questions. It is my understanding that the traditional input-output tables are based on supply use tables, which are based on large-scale surveys.
Right.
Can't the same large-scale surveys be implemented for physical input-output tables? Add a few more rows or columns where you ask them for the values. That is my first question. My second question is, in somewhere in the middle of the presentation, you had mentioned that you had used computational models instead of surveys. So these are established models on what is the input-output across all manufacturing. And my third is there anything that is available for India as of?
All right, all good questions. So for the first question, the discrepancy between physical input output and monetary input output table is a long running debate. So there are a lot of papers out there that talk about that when we take the monetary data and then we put prices, and we convert it into physical, it does not really map. And the reason being that there's subsidies involved. So unless you have a very clear idea of which pricing is applicable on what, then it becomes really challenging. So there is work going on. So there is with Professor Manfred Lenz, and they are working on a top-down approach. So there are two kind of approaches: bottom-up and top-down approach. So in the top-down approach, we take the macroeconomic model and then we put pricing, and we can get the physical. It will just not give you the right structure because sometimes the pricing is off, or sometimes we don't know which are the right suppliers because it's aggregated. The bottom up approach gives us a very fine detail because we can put in the right technology in the right place. So if I know that this is my regional place, then I can look into, there is always, they have to disclose what technology they are using, right? Because it's patented, but they'll not give you the full information, but they'll still give. So that way you can be very confident that we are mapping the right supplier, right kind of technology with the right commodity. So I agree. I mean, there is definitely a way to reconcile or try to reconcile because the bottom up approach will take some time to do the full mapping, but then it also gives more accuracy. So there is a trade off between the accuracy. So it depends on what is your goal.
If somebody wants to compare a monetary input output table and a physical and get the percentage share and the aggregate per unit of consumption production, that would be possible.
Yeah, I think that would be possible. We are actually trying to now look into because we have the USI lab, we are also developing regional economic model, and we are trying to convert that into physical, and then we will compare it with our physical approach to really see what is the discrepancies and differences. So there are like pros and cons, but yeah, that's definitely a thing to think about. So can you remind me of the second question?
Second question is, you had used a computational approach,
Yes.
is what you said, to generate generate large models. So there are established simulations or models which mention the physical inputs in engineering, because the physical input table is mostly related to manufacturing economy.
Yeah.
As per my understanding, there are established models,
Right.
that say that for manufacturing of one car, these are the physical quantities of products starting from rubber and ending with steel. So
Right.
there are already models that exist.
Yes, so there are a lot of models existing, but there are a lot of new models needed. One thing is that industries don't want to disclose their full technology, so that's where we have to go back and actually do. But if we tie up with industries who have the models, it becomes there. So we are actually in conversation of some of the chemical companies who would want to test this approach for their internal supply chains and internal decisions on materials that they need to acquire for future production. So definitely, yeah, there is. But there is definitely a lot of scope for development because some of the sectors that are not very well developed are agricultural and biological. And we are moving towards a lot of biological economy, especially in US, there's a lot of focus on moving towards biological based, waste based kind of economy. So we do need a lot of new models. So some research is required about that. And the third question was,
are there any tables with respect to India?
I think there is input-output table for India, not physical. I'm not aware of. In fact, physical input-output tables are not existent for a lot of places. So I was in conversation with an economist in Netherlands, and he was one of the early pioneers in using physical input-output tables in 1990s. The and I reached out to him asking like, why have we abandoned? And the reason was this, that it's very tedious, and then you cannot validate, and it's very slow. So the cost of making these tables was so high that they did not see value in spending that much time and money. So that's why we have taken a different approach, and we are hoping that because it does have a lot of strength, but it does not, if we spend all our time developing the model rather than using the model, then it becomes waste. So yeah, there are not in PIOTs, and in fact globally, but there is I know European Commission has a project now in developing a full physical map for European Commission. In US we are trying, but I don't know of any other place.
So I have just basic questions because just wanted to know how she is different from the SEEA approach.
Yes.
You might have heard that
Socioeconomic, environmental, yeah.
Ecosystem accounting.
Yeah.
And fundamentally, when you talk of input, output, supply, and use tables, it is the standard template. It's actually the UN model of 2008 SNE. Right?
Yes. Yeah.
I think it's on the same lines, right?
Yes.
It's not
Yes.
something.
Exactly. Yes.
So when it is even in India, like just to add that we have come up with various models on the same SEA approach, but not in a holistic way. In a piecemeal way, we have come up with some of the accounts, and in fact, it was a European Union sponsored thing. Last 7 years we have run, and we have brought it uh, for the for some reverse accounting here. Nonetheless, as you rightly pointed out, it's a very cumbersome, time-consuming, and we are still fighting for the data to come. We have slowly started doing it. This year only we have started Niti Aayog in collaboration with our MOSME and Ministry of Statistics and Programming. So, as you know that it all contains various facets of ecosystem accounting. So we are very soon holding a conference to prioritize what sectors we need to go about with this approach also.
Yeah.
So from once the sectors are identified, I think we will attempt to come out with something like this by next 1 or 2 years.
Oh, that's great. Yeah, that's great to hear. So I think, yeah, that's a good idea too, because we can like think about making it more systematic and more less tedious in time, then we can keep updating, and that would be great.
Great job. So it is something like you are trying to build up a satellite account for the circular economy or the manufacturing sectors, select sectors.
Yes. Yeah. So right now that's the goal, and then going like forward, it's more of like developing the computational infrastructure so that people can start developing more. So if there is an established computational tool and it's well researched and well validated, then people can do it themselves so that we can continue doing it. A lot of times I see in when I had been working on input output since 2007 for my PhD, and one challenge I always faced was the data and then updated models. So that's why I felt that if we can overcome this challenge, all the strengths of these kind of models can be really utilized in long term.
And you can also facilitate crowdsourcing, right? So people can add their data. For example, the question Vishnu asked and what Ramaji said about the construction of this kind of data for India. Even if you have this infrastructure ready, researchers can different people are working on different sectors. They can upload things, validate things on their own. So it can be like a platform or ecosystem where people can.
Only thing is they should know the assumptions made.
Yeah, that can be well documented, and then based on that. But then whatever they do can also be peer reviewed before that can come to the system.
Yeah, so that's why the shared model. Yeah, so the people when share model, we can download and actually go into the model and look. So that's why that's sharing. Some of the industries don't want to share that model, so that's why we have given that option for them to have just an internal modeling system. So the way we are thinking about the computational tool is kind of like a standalone platform technology that people can have in their local area networks who do not want to share anything, but it can also be more open source, right? People just go on the web and do their own. So yeah, it's at early stage, but we are hoping to like scale up the cyber infrastructure. So right now our challenge is developing more models and scaling the cyber infrastructure for it.
But I think you can develop this from the utility point of and the policy formulation for prescription. In addition to the physical, what is being done, if the value add and the actual prices are included in the supply use table, I think that would help immensely the policy makers to come out with any kind of a subsidy or a additional taxation or something of that kind.
Right.
In fact, on that aspect, we have the standard input output tables and models there probably we can link them with this, so that here we can look at the physical economy. Then whatever results we get from here, we can feed it into the economic model, and and from there we can understand the impact on GDP, like you said, tax policies, investment policies. So that is one area probably we can think of collaborating. So I think my experience of using the input-output model, CGE models from an economic point of view, value terms, the main challenge there is when you're thinking about a new technology like electric vehicles or something that doesn't exist much today, and then the accounts won't say much actually. The value accounts won't say much because the production is negligible. Then I think this approach will be really helpful because here you have the technological account of what is needed to make an electric vehicle and so on. And then that from there we can start the economic process as well.
Yeah, so a lot of work has been done for
Yeah.
the new sector.
Mhm.
It is in statistics parlance, it is called the satellite account. What
Yeah.
they have come out is exactly the satellite account for circular economy or satellite account for electric EV sector.
Yeah.
So all that groundwork, I think we have done fantastic for last how many years? 6-7 years.
So this too has been, so it got funded in 2018. So it's been 2, 3 years. But yeah, I started working on physical input output tables in 2011. So 10 years now.
Lot of work has been. So
Yeah.
we can take advantage of that.
Yeah, exactly. That's why we invited her so we can collaborate, continue these collaborations. Any other question? Yeah, any questions from the audience online? Yeah. Any of you, if you have any questions, please unmute and ask. Feel free to ask your questions. So another question I have is, so we talked mostly about specific sectors, and when you talked about Illinois, you are talking mainly about the agricultural sectors, but you also have the rest of the economy,
Yes.
which captures the entire.
Yeah. So that is basically tracking for the commodities. We see that it's not like there's imbalance, which means that we have
Residual.
not modeled that. And that gives us an idea where we need to focus on our modeling efforts in future.
And in that sense, when you talk about a particular commodity, we know the unit, and the units can be different, right? Some can be liters, some can be gallons, some can be
Yes.
square meters. And so on.
Yeah. So that detail is there in the, and we can also go at the elemental level. So I also work on biogeochemistry. So we are also interested in tracking carbon flows and nitrogen flows because it has huge impact on environment as well, like ecosystem. So yeah, so that's something that we need to, of course, like put it in the tool more prominently. That how do you, so adding more functionalities, but it's more like software development.
Right. But like Ramaji mentioned, the satellite accounts, when you also have this value-based input of tables, we also develop some satellite accounts like energy volumes, for example, how much million tons of oil equivalent of coal, oil, gas is needed. And then from there, we compute the emissions because we know per ton of coal burned, and this is the CO2 emissions. And then based on that, we have the emission intensity, and then we have values, then we have these volumes, then emission intensities, and then we develop things. So these are like satellite accounts. So I think here also the approach is similar in that sense, but it's there we only focus on some things like energy, or sometimes we focus on agriculture. We did some work on agricultural commodities, and so on. But here you are talking about many other sectors as well. So
Yeah.
and from a trade point of view, one good thing is we have good data sets on exports and imports at a very detailed level in quantity terms globally.
Oh, that's
So that could be like a good starting point,
Yeah.
and we can make some assumptions for extending them to production and consumption.
Yes.
And so that could be one thing that can be thought about on a
Yeah.
global scale. So
Yeah.
then we can think of a lot of trade policy issues.
Yeah. So yeah, the import and export right now we just upload the data separately, but then we go for the allocation. So we make allocation based on the utilization or the scale of operation. So there's a lot of scope on really understanding how that trade is being utilized in different industries and what are the dependencies. So I feel that there's some research questions that we can focus on allocating the trade data. So there are these models like the gravity-based model where we allocate trade based on the logistics and supply and all that. But yeah, that's an open question. We can definitely do.
Yeah, and one more question, probably there's no straightforward answer for this. Is that in general, in circular economy kind of work, um, there are two sides of the same coin. One is because of circular economy, we were able to increase efficiency, reduce costs, and so on. On the other hand, we are also reducing the demand for some materials, and that's a productivity paradox kind of argument.
Yes.
So typically, if I do this kind of simulations in a CGE model or an input-output model,
Yeah.
it is quite possible that I may get a negative macro impact because some sectors are shrinking.
Yeah.
The positive impact also could happen because of the cost reduction and efficiency increases.
Right.
So have you thought about this, or do you have any ideas here?
Yeah, no, that's a very good point. So we did notice that. So remember that there was urea manufacturing that was reducing
67.
how much it was material providing. So the delta has reduced for that sector, but we can constrain it to make the same thing so we can see the surplus. Because of circular economy, how much surplus is there? Because most of the time our plants are not reduced, right? So we are going to make the same. So that will give us an idea that what is the surplus because of the circular economy that we have in the economy that we can either export or provide to the low areas. So, for example, for us, the fertilizer manufacturing, because of the agro waste, there was a issue of fertilizer reaching different places at the right time, and so that deficit happened. So, if there is a surplus somewhere, we know that this is the region with surplus and it can be provided. So, the region can now establish right trade policies with different region to generate revenue because they implemented circular economy. So if they are investing some money on the circular economy, they also need to recover that money for like generating revenue, right? So it could be by that surplus that they are producing, or it could be just because a shrinking economy is something that no one would do. I mean, I think that's the paradox of circular economy, but it can be it. I think more of it is like redistribution because there are places which are really suffering from not having accessibility to the right technology and right manufacturing practices, and there are places where there's just way too much and they have too much waste, so they generate circular economy kind of thing. Then they still, if their production suffers, then their economy will shrink. Like labor will, there will be unemployment issues, or there will be other kind of taxation issues, and so yeah.
Yeah, actually, one great example is something you already talked about. That is the extraction of rare earth metals from, e-waste and so on, electronic waste and so on. Which is, I think, it's a big thing in the U.S. with the build back better policies that's happening, and here also that's a big focus because there we are not actually displacing any existing industry, but we are developing a new industry.
Yes.
And we are actually creating an effective competition against certain imports.
Yes.
So I think there are some examples like that where circular economy can be directly positive. The thing that is getting reduced is not from the domestic economy but from imports.
Yes.
But so that's an example. But yeah, I think this is a never-ending conversation because we can go back to even labor productivity, for example. Where also you say if the labor becomes more productive, it is likely that you will hire fewer people because one person can do more work now. So there are many such examples. But if there are no further questions, we can end the session and just.
Shall I just have a quick query?
Sure, please go ahead, Balaji.
Yeah, yes. Thank you. My just query is like the Ministry of Statistics for India is releasing supply use table, and latest was till 15/16. The physical IoT is not so far available for India. If we construct the monetary IoT for India for 15/16, and if we try to use some sort of price deflators, then how far it will be feasible to have sort of more reliable PIOT for India? Will it be a right approach, or we should need some adjustment because resources prices are different in different sectors? Will it be a right approach to move towards it, or we need some more modifications? Thank you.
Yeah, I think that will be a good first approximation. So we can start there and then we can look into if that, whatever the structure we get for physical input to output table, if there are discrepancies. So for that, we'll need like domain expertise knowledge for that particular sector. But that would be a good first approximation. So most of the places people are doing that top-down approach. And if you have the right pricing for different sectors at a very disaggregated level, it would be very good. So I think we can move forward with that in if there is nothing else available in the beginning.
Thank you. Thank you.
And just to clarify here, probably we don't need price deflators, but actual prices, right? Because
Yeah.
the values will be in dollars or rupees, and then we need prices, rupee per ton or something,
Yes,
and then
yeah.
then we rather than deflators, we need actual prices.
Yeah, we need actual prices for the transactions.
Okay.
Thank you very much, everyone. And this is
Yes.
a small token of gratitude
Oh,
for
thank you so much. Thank you so much for inviting. It was a pleasure.
Thank you for coming. Please, you can play, say that is also on the CFOs. Thank you.
Thank you.